Ice, ice, baby!
In our last video we dealt with the term time constant, which we need to describe the behavior of circuits where resistors and capacitors influence each other. As we've seen in our first video, the chronoamperometric response of a resistor is a constant current. And if we apply a voltage step to an ideal capacitor, the capacitor is instantly charged. So what happens if the current flows through a resistor and a capacitor that are connected in series? As we see here, the current response shows some characteristics of both resistor and capacitor. The charging of the capacitor cannot be infinitely fast, as the current must flow through the resistor. Instead, the initial current response is controlled only by the resistor. As the capacitor is charged, the current tends towards zero, like we see for the ideal capacitor. So the current decays exponentially if we apply a voltage step to a series RC circuit. Accordingly, we can describe the current response with this exponentially decaying function. How quickly the current decays is governed by the time constant tau, which is the product of resistance and capacitance. The larger the time constant, the slower the process. The time constant has the unit of time. Let's look at how the current response changes if we vary either element, resistor and capacitor, on its own. A smaller resistance allows a higher initial current and the capacitor charges faster. Correspondingly, a larger resistance leads to a lower initial current and slower charging. The charging process has a larger time constant. A larger capacitance does not change the initial current, but it takes a longer time to charge. This too leads to a larger time constant. We can also use the term time constant to characterize electrochemical reactions. A larger resistance might come in the form of decreased electrolyte conductivity. The electrochemical double layer behaves like a capacitor under certain conditions.
In the last video we discussed time constants. However, electrochemical systems can have different time constants, and to resolve them we need to probe the system with signals of different frequencies. And if we plot the impedance for different frequencies, we get an impedance spectrum. Now let's look at two ways to plot such an impedance spectrum. The first way is a Nyquist plot. Here we plot it in the complex plane, where we have the real part of impedance often abbreviated as RE of Z, and the imaginary part of impedance. Which is often abbreviated as IM of Z. However, in electrochemistry, oftentimes we deal with capacitive imaginary parts. And if we recall, the impedance of a capacitor, ZC, is 1 over J omega C, which is nothing but minus J times 1 over omega C. And so the imaginary part tends to be negative, and for convenience sake we often plot the negative imaginary part. However, if we plot it here, it's not immediately obvious at which frequency it was measured. So the second way to plot the magnitude of the impedance and the phase angle over the frequency is the Bode plot. So here we have the frequency, and here we have the magnitude of impedance. which is the absolute of Z. And here we have F. However, oftentimes our measurements span orders of magnitude in frequency and orders of magnitude in the impedance. And this is why we plot this in a double logarithmic form. So we take the logarithm of absolute of Z and the logarithm of F. And likewise, we plot the second parameter, the phase angle, which we call phi. And we give this in degrees here. Last week we had a look at the step response of an RC series circuit. And today I would like to show you the frequency response of this circuit and its composing elements. Here I've brought again the RC series circuit with a resistor of 1 megaohm and a capacitor of 10 nanofarad, as well as its composing elements. This is also a 1 megaohm resistor, and this is also a 10 nanofarad capacitor. And now let's wire them up and measure their electrochemical impedance spectrum. This is a technique where we apply sinusoidal signals of different frequencies, in this case between 1 kilohertz and 1 hertz, and plot the corresponding impedances that we measure with this potentiostat. And so let's begin with the resistor. And what we measure here is a point that is pretty much on the real axis and at 1 megaohm resistance. You see here the real axis, the real part of the impedance Z in ohms, and here the negative imaginary axis, the minus imaginary part of Z in ohms. And as we're now through the entire measurement, we see that the point does not change its location. It's always on the real axis at 1 megaohms. Let's look at the capacitor. Change out the resistor and connect the capacitor. And now I restart the measurement. And this here is only the open circuit voltage as a baseline. And here you can see the impedance spectrum develop. And what you see is, for the high frequencies where the measurement starts, an impedance is measured on the imaginary axis with basically no real component. It's on the zero line here. And with lower and lower frequencies, the imaginary impedance increases. So what results is a spectrum that follows basically the imaginary axis towards ever more negative imaginary values of Z. And now finally, let's have a look at what happens when we combine these two into the RC series circuit, which we've already encountered last week. So, and now onto our final measurement. And what we see is, at high frequencies, the impedance spectrum begins where our resistor was initially, at 1 megaohm on the real axis here, and with no noticeable imaginary component. And as the frequency goes lower, we see that the spectrum behaves like the capacitor did, except that now we have a resistive offset here of 1 megaohm that doesn't change with the frequency. If we look at the Bode plot, what we see here is the logarithm of the magnitude of the impedance, log Z in ohms graphed, against the logarithm of the frequency. So the magnitude here is pretty much around 6, which means 10 to the 6, it's 1 megaohm. And here the frequency from 0, which is 1 hertz, to 3, which is 1 kilohertz. And what we see is that the magnitude decreases for low frequencies, high values of the impedance, to a fixed value of 10 to the 6, the resistor, for very high frequencies. While the phase moves from minus 90 degrees at low frequencies, where the capacitor apparently dominates, to close to 0 degrees at high frequencies, where the resistor seems to dominate.
Hi, last time we had a look at what the electrochemical interface responds to a step potential. This time, for the same system, I have performed a cyclic voltammogram, which you can see here. Here we can see that from minus 200 millivolts up to 0 volts, we see a capacitive response. So now let's have a look at what electrochemical impedance spectroscopy looks like at this potential. Here we've set up the cell the same way like we've done before, with the working electrode made of the stainless steel foil here, the mercury sulfate reference electrode here, and the carbon counter electrode connected here. And the electrolyte is the 1 molar sodium perchlorate solution. Now let's have a look at what the measurement looks like. Here we see the real axis here in ohms, and here the negative imaginary axis also in ohms. We are measuring at minus 200 millivolts, down from 10 kilohertz down to 100 hertz. And the starting points here are the high frequency points, which corresponds to almost 0 on the imaginary axis and around 5 ohms on the real axis, showing resistive behavior. And as the measurement proceeds, you can see that it is increasing on the impedance is increasing on the imaginary axis, which corresponds to capacitive behavior. This is similar to a resistor and a capacitor in series, an RC element. But you can also see here that it shows a non-ideal behavior as we are looking at a real system with a real-world electrochemical interface.
All right, now that we've seen what impedance experiments look like in the lab, let's look at what we expect from these spectra for different elements: a resistor, capacitor, and resistor and capacitor in series. First, the resistor. I will draw a resistor here, and the resistor has an impedance ZR, and this impedance ZR is just R, the resistance. As you see, it's frequency independent. Now let's look at what this impedance of the resistor looks like in a Nyquist and a Bode plot. First, you will see that the Nyquist plot here in this case is square-shaped. This has the purpose of scaling the y and the x-axis equally. So for example, if you were to plot 100 ohms here, you would also plot 100 ohms here, in an effort not to distort any angles of this spectrum, so you can directly see what's going on. However, if you measure the impedance spectrum of a resistor, what you end up with is a resistance, because there is no imaginary part of this impedance. So you measure your first point at any frequency, and it ends up in a distance of R from the origin. And now you decrease the frequency, for example, and you measure again R at this point. You decrease it further. Again, R. Nothing changes. If we plot this in the Bode plot, what we do is we go from the high frequencies when constructing this to the low frequencies. This is inspired by how it's actually measured in the lab. This has the purpose of having the minimum amount of chance for your system to change, because the high frequencies take much less time to measure than the low frequencies. So these at least tend to be ensured in measurement. So you're not waiting for the system to change while you measure before you measure the high frequencies. However, for the resistor, the magnitude of the impedance stays constant over the frequency because, of course, there's no frequency dependence. So let's just plot it here as a constant line. And of course, the spectrum is discretely measured in the lab. But in actual reality, it's a constant spectrum. So in the Bode plot, I will just draw this as a straight line. And this here is ZR. And because it's logarithmic, it's log R. The phase angle for any frequency is 0 degrees because a resistor does not induce a phase shift. Now let's move on to a capacitor. This is slightly more interesting. The capacitor has an impedance ZC. And this impedance of the capacitor, ZC, is 1 over J omega C equals minus J times 1 over omega C. Now let's think about this function. For very high frequencies, this term gets low and approaches 0. For very low frequencies, this term goes towards 0 because the frequency goes towards 0, and this term gets very high. This makes a lot of sense intuitively. If you think about when you charge a capacitor and you apply a sinusoidal voltage. And so consider every time you want to go from one peak to the next of the sinusoid, you have to bring a fixed amount of charge to the capacitor to charge it, to establish the voltage. And if you do this much more often in 1 second, then of course you need a higher current to deliver the same charge in a lower amount of time. And this expresses itself in having a higher current for the same voltage peak you apply when the frequency is high. If we plot this now in the Nyquist plot, what we see is this impedance only has an imaginary part. There's no real part. Everything that's written here is multiplied by J. And so we go. We begin with high frequencies. The impedance is low because we draw a rather high current. And then we decrease the frequency, and we again measure an imaginary impedance that just gets larger. Larger and larger and larger as the frequency gets lower. If we plot this in a Bode plot, what we have is, for first, a constant phase angle. This impedance is always imaginary. And you see all of these impedances have a 90-degree phase shift here, all one over the other. So this is easy to draw. The phase angle is minus 90 degrees, and it's constant. Let's imagine that my drawing skills show this as constant. However, the magnitude of the impedance changes, as we've just discussed. And what this means is for high frequencies, it gets lower. And this expresses itself in a rising function. Now, what happens if we have a capacitor and a resistor in series? What we have is first a resistor with its impedance ZR, and a capacitor which brings its impedance ZC. And in a series connection, both of these impedances add. ZRC is nothing but the sum of ZR plus ZC equals R plus 1 over J omega C, which if we write it like here is of course the same as R minus J times 1 over omega C. So what has changed? Compared to here, what has changed is that we've introduced a real part, and the real part is the resistance R. However, this real part here is not a function of frequency. The real part stays constant, because the resistance stays constant. Only the imaginary part is a function of frequency. So what we have, essentially, is ZR is just ZR, but ZC is a function of frequency, and consequently ZRC is also a function of frequency. If we plot this in the Nyquist plot, for very high frequencies, we again get the same pattern as here. We get a resistance offset here on the real axis. Except that now we're not just stuck with the real part, but we also have some imaginary part from the capacitance. So for high frequencies, the first point may be here, at this point. And now as the frequency gets lower and decreases, we go in a straight line up here, where the resistance, the real part of impedance, stays constant, and the imaginary part gets higher and higher. For the Bode plot, this gets more interesting still. If we have very high frequencies, let's think about what happens to this term over here. For very high frequencies, 1 over omega c is very small, because the omega is in the denominator. For high frequencies, this is large, so this part is small. And what happens is that R is consequently much more dominant than this small term. And what we have is a phase angle that is largely 0 degrees, because this is much larger than this part. And also, the magnitude of the impedance is pretty much R. So we begin with a phase angle at high frequencies for 0 degrees, and with a magnitude of impedance that is somewhere here at R. If the frequency now decreases, at some point this part gets on the order of magnitude of the R and becomes relevant. And so what happens is that the magnitude of this total impedance begins rising, and the phase angle moves closer to the minus 90 degrees dominated by the capacitor, until for very low frequencies, finally, this imaginary part, 1 over omega c, is much larger than the resistance and becomes dominant. So at some point, the phase angle will approach minus 90 degrees for low frequencies. Consequently, we get this kind of shape here, where this is minus 90 degrees. The impedance for some frequency here begins rising. And then it just continues rising like we've seen from the capacitor. So these are the spectrums that we expect for a resistor, capacitor, and resistor and capacitor in series, where they both add